What if the most profound secrets of the universe aren't unveiled by grand telescopes pointing skyward, but by pure, unadulterated annoyance? The year was 1964, a time when the world was gripped by the Cold War, a tense standoff between global superpowers. In the quiet, rolling hills of Holmdel, New Jersey, far from any traditional observatory, stood a peculiar horn antenna, a legacy of Bell Laboratories' ambitious Project Echo. This cutting-edge instrument was initially built for pioneering satellite communications, a vital step in the race for global connectivity. It was here that two brilliant radio astronomers, Arno Penzias and Robert Wilson, found themselves in a frustrating battle against an invisible enemy. Tasked with repurposing this massive antenna for scientific observations, they were plagued by a persistent, faint, and utterly uniform background hiss, an unwanted cosmic static that simply would not vanish. This wasn't the distant chatter of human communication they were seeking. It was an omnipresent whisper emanating from every direction of the sky. They meticulously recalibrated every dial, checked every cable, and examined every circuit, convinced it was an artifact of their own equipment or some local interference. Their efforts to eliminate this persistent noise bordered on the legendary. At one point, suspecting the signal originated from within the antenna itself, they famously climbed inside the colossal horn, diligently scrubbing away years of accumulated pigeon droppings. They even tried to evict the pigeons, only for the birds to return, undeterred by the indignity of their eviction. Yet, even with the antenna sparkling clean and the pigeons banished, the maddening, inexplicable hiss remained, a uniform whisper at an equivalent temperature of approximately 3.5 Kelvin. It was a mere whisper, yet it was everywhere, unwavering. This relentless pursuit of a technical nuisance, inadvertently funded by the geopolitical tensions of the space race and the urgent need for global communication channels, was about to stumble upon something far more profound than any satellite signal. The narrative shifts from a story of technological troubleshooting to a cosmic detective tale, beginning with a seemingly innocuous phone call. Arno Penzias, bewildered by the stubborn noise, reached out to physicist Bernard Burke, who in turn connected him with Robert Dickey's team at nearby Princeton University. The irony of what unfolded next is a classic in scientific history. Miles away, at Princeton, Robert Dicke and his esteemed colleagues, including Philip James Edwin Peebles, Paul Roll, and David Wilkinson, had independently theorized the existence of a faint, relic radiation left over from the very beginning of the universe. This afterglow of the Big Bang was precisely what they were actively building their own detector to find. They were on the verge, methodically constructing their equipment, when Penzias and Wilson's accidental encounter scooped their anticipated triumph. The realization must have been a bittersweet moment for Dicke's team, their theoretical predictions confirmed not by their own grand search, but by someone else's exasperated technical troubleshooting. The core significance of what Penzias and Wilson found was not just its accidental nature, but the inherent characteristics of the signal itself. This cosmic static, now known as the cosmic microwave background, or CMB, was an astonishingly precise thermal glow, measured at 2.725 Kelvin. Crucially, it exhibited an almost unbelievable uniformity across the entire celestial sphere. The temperature variations were incredibly minute, fluctuating by only 1 part in 100,000. To fully grasp this, consider the surface of a perfectly smooth billiard ball. If you were to scale that ball up to the size of the entire Earth, the largest deviation from perfect smoothness would be no more than a few meters. That is the kind of incredible precision reflected in the early universe's temperature map. This near-perfect smoothness posed a monumental challenge to the prevailing cosmological understanding. Cosmologists had long envisioned the universe's fiery birth as a chaotic explosion, a Big Bang that should have left behind a much lumpier, more uneven thermal imprint. Yet here was evidence of an almost pristine, unsettlingly smooth blueprint. It was a clue that seemed too perfect, a piece of evidence that, instead of providing answers, spawned a cascade of profound new questions. This cosmic static was not just leftover heat, it was a message, a pristine blueprint from the infant universe itself. Its perplexing, almost impossible uniformity was the first major crack in the standard Big Bang theory, hinting strongly that a dramatic, hitherto unknown event must have preceded the universe as we understood it. This central enigma, a universe too perfect, would haunt cosmology for the next decade and a half, transforming what began as a tale of technological troubleshooting into the opening act of a cosmic detective story. This wasn't just a faint whisper, it was the echoing silence of a beginning that, according to the physics of the time, simply should not have been possible. The universe, as we observed, presented an impossibly perfect face, a cosmic echo, uniform across the vast celestial tapestry, its temperature variations no more than 1 part in 100,000. This wasn't a sign of elegant simplicity. For the physicists of the 1970s, it was the opening act of a terrifying cosmic nightmare, a series of paradoxes that threatened to unravel everything they thought they knew about the Big Bang itself. These were not abstract theoretical concepts, but agonizing puzzles that kept brilliant minds awake at night, staring at equations that simply refused to balance. One of the most unsettling of these cosmic enigmas was the horizon problem, articulated by physicists like Charles Misner in the late 1960s. It asks a deceptively simple question. How could two regions of the sky, lying on opposite sides of our observable universe, possess the exact same temperature? To grasp the profundity of this, consider two individuals positioned at the absolute farthest ends of an immense, utterly dark room. They have no way to see each other, no means to communicate, no light that has ever traveled between them since the moment they arrived. Yet, somehow, they have managed to perfectly coordinate their outfits, down to the exact shade of their socks. In the early universe, light, the fastest messenger we know, simply had not had enough time to travel between these vast, distant regions. They were never in causal contact, meaning no information, no heat, no energy could have passed between them to equalize their temperatures. The Big Bang model, in its raw form, offered no mechanism for such a synchronized, uniform heat distribution across a universe that was, in its earliest moments, far too expansive for its parts to communicate. This homogeneity was, by all accounts, an impossibility. Then came the flatness problem, a challenge to the very geometry of our cosmos. Our universe, on its largest scales, appears to be remarkably, almost miraculously, flat. Think of a sheet of paper stretching infinitely, not curved like a sphere or a saddle. This flatness is a state of profound cosmic instability, as precarious as attempting to balance a perfectly sharpened pencil on its tip for a staggering 13.8 billion years. Any minuscule deviation from perfect flatness in the universe's earliest fractions of a second, an infinitesimally slight curve in either direction, would have been magnified exponentially over cosmic time. Had it been ever so slightly positively curved, it would have collapsed back in on itself almost instantly, long before galaxies could form. Had it been even a whisper negatively curved, it would have expanded so rapidly that matter would have dispersed into a cold, empty void, incapable of coalescing into stars and planets. The survival of our universe, its very existence as a place capable of supporting life, therefore implies an act of cosmic fine-tuning of unbelievable precision, a precision that Robert Dicke, a pivotal figure in identifying this problem, found deeply troubling. The initial conditions had to be set with an accuracy of something like 1 part in 10 to the power of 60, a number so astronomically large it defies human comprehension. And as if these two nightmares weren't enough, grand unified theories, or GUTS, which sought to describe the universe's fundamental forces at ultra-high energies, introduced a third, equally perplexing puzzle, the magnetic monopole problem. These theories predicted that the incredibly hot, dense crucible of the very early universe should have been absolutely flooded with incredibly heavy, stable magnetic monopoles, particles carrying an isolated north or south magnetic pole, unlike ordinary magnets which always have two. They are theorized as cosmic relics, forged in the universe's infancy, that should have survived to this day. Yet, despite decades of relentless searching, using instruments ranging from particle accelerators to sensitive detectors deep underground, we have never, not once, observed a single magnetic monopole. The standard Big Bang model provided no natural way to dilute or eliminate these predicted relics, leaving cosmologists scratching their heads as to why the universe wasn't teeming with them. The collective weight of these three paradoxes, the horizon problem, the flatness problem, and the magnetic monopole problem, created a profound philosophical discomfort. It flew in the face of the Copernican principle, which gently reminds us that Earth is not the center of the solar system, our solar system not the center of the galaxy, and our galaxy not special in the cosmos. Yet, these problems implied that our universe was extraordinarily, improbably special, fine-tuned to an absurd degree. It was as if humanity had won a cosmic lottery with odds so astronomically low, far beyond winning every lottery on Earth simultaneously for 1 billion years, that it suggested the game itself must have been rigged. The standard Big Bang model, a triumph in so many other ways, offered no answers, no escape from this growing impasse that gripped cosmology by the late 1970s. The universe's perceived perfection was not a sign of elegant design, but rather a glaring symptom of a deep, undiscovered secret lurking in its earliest, most mysterious moments. The universe's impossible perfection, a riddle that had confounded cosmologists for more than a decade, begged for a solution. But where could such an answer possibly come from? Not from the distant glint of a telescope pointing skyward, nor from complex calculations based on the observed cosmos. Instead, the profound secret to our universe's improbable existence was unearthed in a realm seemingly unrelated, the high-energy world of particle physics, in the late 1970s. It was a place of invisible forces and infinitesimal particles, a world probed not by astronomers, but by theorists delving into the very fundamental nature of reality. At the heart of this unexpected convergence lay the ambitious quest to unify the universe's fundamental forces. Physicists were grappling with grand unified theories, often simply referred to as GUTs, a bold attempt to weave together the strong, weak, and electromagnetic forces into a single, elegant framework that would operate at the immense energies present in the universe's earliest moments. It was within this highly theoretical landscape that a young postdoctoral researcher at Cornell University named Alan Guth found himself in 1979. He was not, at that time, consciously trying to resolve the cosmic paradoxes that plagued cosmology. His focus was entirely on exploring the intricate consequences of these grand unified theories, specifically a concept known as a phase transition. To understand this crucial idea, consider a familiar earthly phenomenon, the transition of water into ice. As liquid water cools, it reaches a critical temperature and undergoes a dramatic change, solidifying into ice. This process isn't just a physical alteration. It releases a significant amount of latent heat, energy that was stored within the liquid structure. Guth, collaborating with his contemporary Henry Tye, hypothesized that the early universe might have undergone a similar, albeit far more extreme, phase transition as it rapidly cooled from its initial superheated state. The critical insight was that, under certain conditions, this cooling universe could get stuck in a supercooled, high-energy state. Physicists termed this peculiar state a false vacuum. The defining moment for Alan Guth arrived late one night, a classic eureka experience, born from a deep dive into his calculations. He realized, with a jolt of sudden clarity, that this trapped energy within the false vacuum, this supercooled state of the early universe, possessed an utterly incredible property. It would act, in essence, as a form of anti-gravity. This wasn't merely a theoretical oddity. It meant that the very fabric of space itself would be compelled to expand at an exponential, mind-bogglingly faster-than-light rate. This phenomenon, which he christened inflation, was initially just a curious, unexpected side effect of his complex particle physics equations, a theoretical ripple in the fabric of his abstract work. Yet, as with many profound scientific breakthroughs, the seeds of this idea were not sown in isolation. Half a world away, often overlooked in Western historical accounts, crucial independent work was unfolding. In Moscow, at the Lebedev Physical Institute, the brilliant Soviet physicist Andrei Linde was independently developing strikingly similar ideas about the universe's rapid early expansion. Even earlier, in 1979, Alexei Starobinsky had proposed a model describing an early exponential expansion rooted in sophisticated quantum gravity considerations. This remarkable convergence of thought, separated by political and geographical divides, highlights the sheer power of scientific inquiry and the cross-pollination of ideas, even when direct collaboration is limited. The beauty of inflation was its sheer elegance in resolving the universe's most pressing paradoxes in one astonishing stroke. Remember the horizon problem? The baffling uniformity of the cosmic microwave background across regions that should never have communicated. Inflation provided the answer. It stretched an infinitesimally tiny, causally connected patch of the primordial universe, a region perhaps smaller than a single atom, to become larger than the entire observable universe we see today. Every part of this vast cosmic expanse was once intimately connected, homogenized by a rapid, shared expansion, before it grew too large for light to traverse. And what of the flatness problem, our universe's precarious balance, like a pencil on its tip? The same exponential stretching process during inflation acted as a cosmic iron. Any initial curvature, no matter how pronounced, would be flattened out to an almost unimaginable degree, leaving behind the nearly perfectly flat geometry we observe. This extreme expansion also offered a neat solution to the magnetic monopole problem. If these elusive, super-heavy particles were indeed created in the early universe, inflation would have diluted them to an extraordinary extent, spreading them so thin across an immensely expanded volume that the probability of detecting even one would be astronomically low. The solution to cosmology's deepest riddles was not found by gazing up at the majestic night sky, but by looking inward, delving into the very fundamental nature of matter and energy at its most extreme, most primordial level. The universe, a symphony of stars and galaxies, seems like a grand, ordered masterpiece. But how did such immense structure emerge from a primordial void that, by all accounts, should have been utterly smooth and featureless? The solution, as baffling as it is brilliant, lies not in some external force, but within the very essence of empty space itself. After understanding the why of cosmic inflation, how it elegantly solved the universe's great paradoxes, we must now confront the even more mind-bending how. This journey takes us into the engine that powered the universe's exponential expansion, a mysterious entity known as the inflaton field. This isn't some abstract mathematical construct. It is a hypothetical scalar field, not unlike the Higgs field we have recently discovered, a fundamental aspect of reality that permeated every single point of space during the universe's infancy. In the first fleeting fraction of a second, before light could even traverse the smallest imaginable distance, this field held an immense amount of potential energy. Instead of being a given, something simply there, we can connect it to a more tangible yet equally perplexing idea from quantum mechanics: the inherent energy of empty space, or what is often called vacuum energy. Even what we perceive as perfect stillness, the ultimate vacuum, is, at its most fundamental level, a seething cauldron of activity. Dive deep enough, to scales far beyond the reach of any instrument, and you encounter what physicists call quantum foam. Here, guided by Heisenberg's uncertainty principle, virtual particles constantly flicker into and out of existence, borrowing and repaying energy from the vacuum in an endless, fleeting dance. This is not stillness. It is an unseen, roiling ocean of potential, alive with infinitesimal, fleeting quantum fluctuations. Inflation, this incredible epoch of faster-than-light expansion, acted as the ultimate cosmic microscope. It took these infinitesimal, fleeting quantum fluctuations, mere whispers in the cosmic void, and stretched them to astronomical, universe-spanning proportions. The tiny ripples in the inflaton field, these quantum jitters born from the inherent uncertainty of reality, were not merely present. They were magnified exponentially during the inflationary epoch, becoming imprinted onto the very fabric of the expanding cosmos. In 1981, in the Soviet Union, Vyacheslav Mukhanov and Gennady Chibisov, working at the Lebedev Physical Institute, made a groundbreaking calculation. Independently, a year later, at the Cambridge Nuffield Workshop in 1982, a team including the legendary Stephen Hawking reached similar profound conclusions. They precisely calculated how these quantum jitters, these tiny ripples in the inflaton field, would not only be magnified, but would be imprinted onto the very fabric of the expanding cosmos. Their work showed that what began as microscopic uncertainties would be stretched into macroscopic density variations. These stretched-out quantum jitters, once microscopic, became the primordial seeds of all structure we observe today. Think of them as tiny variations in density, minuscule cosmic hills and valleys in an otherwise smooth expanse. Regions that were infinitesimally denser than their surroundings began, over cosmic eons, to exert a stronger gravitational pull. Like cosmic magnets, they slowly attracted more and more matter, growing into the immense structures we now call galaxies, clusters of galaxies, and eventually the very stars and planets that compose our observable universe. Consider the Hercules Corona Borealis Great Wall, a supercluster of galaxies spanning 10 billion light-years across. This gargantuan structure, one of the largest known in the cosmos, is not merely a collection of stars. It is a fossil, a direct macroscopic echo of a quantum event that occurred during the universe's first 10 to the power of -32 seconds. To grasp that scale, that is 100 million millionths of a second. It is like finding the blueprint of a skyscraper on a single atom, then seeing that atom stretched across an entire continent, carrying the exact same information. Advanced simulations allow us to witness this transformation in cosmic time. We begin with a universe that appears perfectly homogeneous, a canvas of pure cosmic uniformity. Then, as the stretched quantum fluctuations are imprinted upon it, we see the subtle variations emerge. Over billions of years, gravity then takes hold, slowly sculpting these tiny imperfections into the complex, intricate, web-like cosmic structure that permeates the universe, resembling a vast, luminous neural network. Our entire existence, from the smallest atom to the grandest galaxy, is therefore a direct, macroscopic manifestation of the inherent, irreducible uncertainty of the quantum world, forged in the crucible of inflation. The universe, a canvas of cosmic echoes, holds secrets etched into its very fabric. We have explored how an astounding period of faster-than-light expansion, known as inflation, might explain the universe's puzzling perfection and the vast structures we observe today. But if this cataclysmic event truly occurred, if it stretched spacetime itself by an unimaginable factor, then it must have left behind more than just a smooth, flat cosmos. It must have violently shaken the very foundations of reality, sending ripples across the nascent universe like a stone dropped into a cosmic pond. These ripples are known as gravitational waves, distortions in the fabric of spacetime itself, and the hunt for their primordial echo represents one of the most thrilling, high-stakes detective stories in modern astrophysics. Scientists theorize that these ancient gravitational waves would have imprinted a unique, faint, swirling pattern on the oldest light in the universe, the cosmic microwave background. This specific pattern is called primordial B-modes. They are the cosmic equivalent of fingerprints left behind at the scene of the universe's birth, a telltale sign that only the immense, violent stretching of inflation could have created. Finding this particular signal would not merely support the theory of inflation, it would provide near irrefutable proof, transforming a powerful theoretical construct into an observed, undeniable fact. The scientific community was electrified in March of 2014. At a press conference held at the Harvard-Smithsonian Center for Astrophysics, a team working on the BICEP-2 experiment, located at the remote and frigid South Pole, announced a monumental discovery. They had detected what appeared to be the exact swirling B-mode pattern they were seeking, a signal seemingly plucked directly from the dawn of time. News outlets worldwide hailed it as Nobel Prize-worthy, a breakthrough that promised to rewrite the textbooks and unlock the universe's deepest secrets. The excitement was palpable, a collective gasp of wonder rippling through researchers who believed they had finally gazed upon the first moments of cosmic creation. It was a moment of triumph, a glimpse into the very first tiny fraction of a second of the universe's existence. Yet in science, extraordinary claims demand extraordinary evidence, and the scientific method is a relentless, self-correcting engine. Following the initial euphoria, a period of intense scrutiny began. Other scientists, particularly those operating the European Space Agency's Planck satellite, whose mission was to map the cosmic microwave background with unprecedented precision, began to meticulously cross-reference the BICEP-2 data. Planck had its own observations of polarized light, and its instruments were designed to filter out interference from within our own galaxy. The question arose, could the detected signal be something other than a primordial echo? Over the following months, a humbling but ultimately powerful truth emerged. Through careful collaboration, including work with the BICEP-2 team itself, it was eventually demonstrated that the signal, though real and precisely measured, was not from the dawn of time after all. Instead, it was caused by polarized light emanating from interstellar dust within our own Milky Way galaxy. This was not a failure of the scientific method, it was its magnificent triumph. It showcased its demand for rigorous verification, its unwavering commitment to objective truth, and the profound importance of collaborative scrutiny in pushing the boundaries of human knowledge. The initial excitement gave way to a deeper understanding, reinforcing the principle that science constantly refines its conclusions based on new evidence. But the hunt did not end there. Far from it. The experience with BICEP-2 only sharpened the resolve of scientists. Today, the quest for primordial gravitational waves continues with even greater sophistication. Next-generation experiments are rising in the most pristine corners of our planet. Consider the Simons Observatory, nestled high in the Atacama Desert of Chile, where the dry, clear air provides an unparalleled window to the cosmos, or the South Pole Telescope, still operating in the frozen Antarctic, continually pushing the boundaries of detection. In the future, missions like the Light-Bird satellite, a dedicated space observatory, will take the search beyond Earth's atmosphere, where galactic dust poses less of a challenge. This ongoing effort can be viewed as a high-stakes archaeological dig, where scientists are developing ever more sensitive tools, instruments capable of sifting through the faint galactic foreground, patiently searching for that elusive, primordial echo of the universe's very first moments. The signal is incredibly faint, buried beneath layers of astrophysical noise, but its discovery would fundamentally alter our understanding of cosmic origins. The hunt is still on, driven by the profound realization that, if successful, it would transform inflation from a compelling theoretical framework into an undeniable observed fact of our universe's violent and mysterious birth. What if the universe, in its dizzying expanse of galaxies and shimmering nebulae, is not a singular, isolated entity, but merely a single, fleeting breath in an infinite cosmic exhalation? For decades, our understanding of the cosmos has expanded, pushing the boundaries of what is conceivable. But the inflationary paradigm, if truly correct, does not just explain the universe we see, it forces us to confront a reality far grander, and perhaps far more unsettling, than any science fiction. It suggests that our entire existence, every star, every atom, every moment of time, might be just one bubble in an eternal frothing cosmic foam. This radical idea finds its most profound articulation in the work of the brilliant Soviet physicist Andrei Linde. In the mid-1980s, as a key architect of the inflation theory, Linde began to explore its ultimate logical consequences. The quantum fluctuations, those infinitesimal jitters in the primordial inflaton field, are not merely responsible for seeding galaxies. In many models, these same quantum uncertainties can affect the inflaton field itself, preventing inflation from simply stopping everywhere. Instead, it might only cease in specific, localized regions, while continuing eternally in others. Consider a pot of water brought to a rolling boil. As the water heats, bubbles form, expand, and then, upon reaching the surface, they burst, releasing their steam and cooling. Our universe, in this mind-bending analogy, is just one such bubble. It formed, expanded rapidly, and then cooled down, allowing stars and galaxies to coalesce. But the water around it, the surrounding background of the inflaton field, continues to boil, eternally generating new bubbles, new universes, in an endless succession. This process, known as chaotic eternal inflation, paints a picture of a vast, fractal-like structure, a multiverse, where universes are constantly being born from the ever-inflating spacetime. This is no whimsical fantasy dreamt up by a curious mind. This concept emerges as a direct, logical, and perhaps unavoidable consequence when the principles of inflation are combined with the inherent uncertainties of quantum physics. It is the universe's most extreme form of creative self-replication. Each of these new bubble universes, freshly spawned from the eternal background, might cool down and settle into dramatically different states. They could possess different fundamental constants of nature, the speed of light, the strength of gravity, the mass of an electron, all potentially varying from one bubble to the next. Their physical laws could be entirely alien to our own, dictating a cosmos where matter behaves in unimaginable ways. Some might even have a different number of spatial or temporal dimensions. The possibilities spiral into an almost infinite array of realities. This staggering concept offers a potential, albeit highly controversial, answer to one of the most vexing cosmic paradoxes, the fine-tuning problem, that cosmic lottery where our universe appeared almost miraculously perfect for the emergence of life. If there exists an infinite ensemble of universes, each with its own unique set of physical laws and constants, then it is no longer so miraculous that at least one of them, like our own, happens to have precisely the right conditions for stars, planets, and even consciousness to arise. We find ourselves in a universe suitable for life simply because we could not exist in any of the others. Our very presence here is evidence of a selection effect, akin to finding yourself in the one winning lottery ticket out of an infinite number of possible tickets. This extends the Copernican principle, which has progressively humbled humanity's place in the cosmos. First, our planet was not the center of the solar system. Then, our solar system was not the center of the galaxy. Our galaxy itself proved to be just one of billions. Now, this ultimate extension suggests that not only is our planet not special, nor our galaxy, but perhaps our entire universe and its fundamental physical laws are not unique. We may simply be an unremarkable outcome in a vast, endlessly diverse cosmic landscape. It is crucial to maintain a careful scientific tone when contemplating such profound implications. The multiverse, while a compelling and logical consequence of many inflationary models, remains currently an untestable metaphysical consequence of the theory, not a proven reality. We lack direct observational evidence of other bubble universes, and the very nature of their separation from our own makes such observations incredibly challenging, perhaps even fundamentally impossible. Yet, the theoretical framework that leads to this conclusion is robust, rooted in our best understanding of particle physics and cosmology. So, the journey that began with a mysterious, faint hiss in a radio antenna, a seemingly insignificant technical nuisance, has led us to the precipice of an almost inconceivable thought experiment. It ends not with a definitive answer, but with a profound and humbling question. Our entire cosmos, with its billions upon billions of galaxies, its unfathomable distances, and its intricate dance of matter and energy, might be just a single, fortunate outcome in an eternal, creative reality far grander and stranger than we ever dared to imagine.